Hi, welcome to Turkish Engineering. In this lecture, we are going to solve problems related to Chapter 4. So, we just explained the basics for Chapter 4. Now, we will solve all problems for our 6 parts of Chapter 4. So, in the first part, we will take net force and 2 examples for net force. So, this is the first example. We have a weight which is coming from the leg, and to carrying this leg's weight, we have 2 ropes which is attached by 2 masses. So I know the first mass, which is 110 newtons, and here I have the second weight which has an angle here. So the question is asking for both 2 unknowns, the angle and the weight. It's a little bit challenging problem, but you will see that it's not too hard. So let's start by one of the axes. I can start by x-axis or y-axis. So since the leg is in an equilibrium case, there is no motion. It will be at rest, right? So in this application, it's a medical application, I must have this leg in a stable case, in a static case. So it will not move. That means when I take this point and put the free body diagram, I must have just balanced forces. I must have balanced forces in both 2 axes. So this is the first force which is coming from T2. I can put here T2. Okay, this is T2. And as you see here, I will have another T2. From this free body diagram, which is between weight 2 and the rope, you will say that T2 will be equal to weight 2. So the force which is pulling in this way from the rope, it will be just tension 2, and this tension 2, because of the same rope, is just being pulled by this weight. So you can say that the weight is equal to tension. And here the similar case. So you will have just a tension. Say that it's tension 1. So here you have tension 1, the same tension, because you have the same rope here. So this tension 1 from this free body diagram, which can be taken from this, you will say that T1 equals to 110 newtons. But I don't know weight 2, so T2 also, and I don't know what's alpha, but I know the angle which is 40 degrees. So let's put T1 to find the real angle. Here I know that it's 40 degrees, but I must use the angle which is coming from positive x-axis. So I must use this one. Actually, this one is 180 minus 40, which will be just 140 degrees. So for calculating T1 components, I will use this angle. I have T1 here, and I have weight 1. So weight 1, which one I know? Weight 1 is just this. 220 newtons. So let's start by one of the axes. I will put the which one? I will put the x-axis. So let's start. So Rx, which is, or we can use this one or this one. They are all representing the same idea, the net force in the x. Since there is no acceleration in x, I will put the acceleration. This is the formula which is coming from second law, but there is no acceleration in x, so I will say that they must be equal to 0. So what are the forces in the x-axis? What are the forces which are acting in the x-axis? So you have here alpha, and the other angle which is from here to there is 140. So the first force will be tension 1, but the component in the x-axis, so you will take the cosine. So this is the first force, plus the second force, which is just T2 cosine of alpha. But I don't know T2 and I don't know cosine alpha. So actually you can say just T2x, and T2x will be equal to just T cosine theta. T cosine alpha. But I will just put here T2x. You will see why I'm putting T2x, because I must calculate the x component, then y component, so I can calculate the alpha. The alpha will be easy calculated, but firstly I must know this one and t2y, so I will be able to calculate the alpha. Let's put the other axis. So I will have this equilibrium case, which is static case in the second axis, which is the y-axis. So I have negative 220, which is pulling down the weight, and two forces which are acting in a positive way. Actually, instead of putting this one, you can put this one, positive of weight, V1, but put the angle. So sine of what? You want to take the y component, right? So put sine of, but your angle is minus 90, right? So when you put minus 90, you will get, you will get negative. Negative weight 1 will give you negative 220. But actually in this case, you don't need to make these calculations, because you are seeing that it is just only pulling down. So the weight is pulling down. It's only in the y-axis and a negative sign. So you will put negative here. It is easy. What about these two? So I have t1 sine of this one plus t2y. So I have two equations and two unknowns. So to solve this system of equations, I must reduce my unknowns from 2 to 1. So I will put this t2x in terms of t1. Okay, so when I see here, actually I have three unknowns here: t1, t2x, t2x and t2y. So I made a mistake here. I put t2x and I didn't put t2. So I will put, actually let's make it here the same one, but I will need an extra knowledge. What can it be? So I have three unknowns. It doesn't matter, no problem. But I must have a third equation. Actually, the third equation is coming from here. I forgot that we know t1. So actually, in this case, we don't have three unknowns. We have only two unknowns, which is t2x and t2y. But I forgot that t1 is known because it's given here, just 110. So let's go back. So in fx, y equals to 0, so t1, which is just 110 cosine of this one, plus t2x. So you will see that t2x will be equal to minus 110 cosine of 140. So let's calculate the first force. Minus 110 multiplied by cosine of 140, just 40. So you will get, because of the cosine of this one will have positive sign, so you will get cosine of 140 will give you negative sign. So negative multiplied by negative will give you positive. So it is 84.3 newtons. So the first force is calculated. What about the second one? So in Fy, I have 0 equals to minus just 220 plus this one, which is just 110 sine of this one, will be equal to t2y. So t2y will be equal to, just this will be go to other side, so positive side, minus this one positive, so for the other side will be negative. So you will see the answer. I have 220 minus 110 sine 140. So I will get 149.3 newtons. So now I know t2x, which is the x component, and I know t2y. So I can put the vectors. So I have t2x, which is this one, and I have So I can calculate for T2. It will be just T2 will be equal to T2x squared plus T2y squared in a square root. So it will be just this one plus the other one squared. So I will get T2 will be equal to what? Let's calculate it. Squared plus. So I will get 171.5 newtons. So I know T1. I know tension 2. But what about this angle, which is alpha? How can I calculate the alpha? The alpha will be equal to this one. The inverse tangent of opposite one divided by adjacent. So T2y divided by T2x, which is equal to arctangent of 149.3 divided by 84.3. So I will calculate the angle. Arctangent, which is shift tangent, and put your values. So it is just 60.5 degrees. So as you saw, we solved for two unknowns, and since we have two equations, one of the equations in x-axis and the other one is in the y-axis. So this is the problem. Why I put here T2x and here T2y? I didn't put T2 cosine alpha and here T2 sine alpha. Actually, the unknowns will be 3, and I have two equations, so it will be just more complicated. So I put T2x to find just the x component of the tension, and I put here T2y to find just the y component. If I know the x and y components, I can calculate for the resultant force of T2, which is the T2, the total T2, and I can calculate for the angle by inverse tangent. So this is the idea. The last force for the net forces. So we have two-dimensional tug-of-war. So Charles is pulling in this way, and Alex and Betty is pulling down. And I know that the angle between Betty and Alex is 137. So here the same case. Here I have an alpha, or let's say theta, but I don't know what's theta. But the angle, just put the x-axis and y-axis. Okay, the angle which is Alex pulling, so it is just 90 degree plus something. I don't know this one. Actually, as you see here, this is a total 180 degrees, but you will subtract this one. So it's about 43 degree, right? Here you have 43 degree. So the Alex push, Alex pull will has this angle. So it is just 90 plus 43 degree. That means 133 degree. This is for Alex. And Betty is pulling down. So it is negative 90 degree, and Charles is pulling in this way. So by angle theta, this is Charles. I must calculate what I must calculate. Let's see. Alex pulls with a force of 220. So this is known. Alex will be just 220 Newton. And Charles is 170 newtons, but Fc, which is Betty's force, yes, Fc, Fc is not given. The direction of Fc is not given. So Charles, this angle, which is theta, is not given. So this is one of the unknowns. And the second unknown is Betty's force, Fb, which is this one. It's unknown. So I must calculate what's the Betty's force for equilibrium case and what's the Charles angle. So how can I calculate? I must put two equations for two axes. So I will start by x-axis. In x-axis, the summation of all forces must be equal to 0. I have two forces which have the Charles pulling force in the x-axis, which will be just the force multiplied by cosine theta. I have Alex forces. I will put positive, but from the angle I will get negative. You will see. Alex force, which is just 220 cosine of this degree. So you will say that for calculating cosine theta, this is unknown. If I know cosine theta, I can calculate for theta. So let's first calculate cosine theta. How can I calculate cosine theta? So let's move this one to the other side. So this one will be equal to minus 220 cosine this one. So when you divide both sides by 170, you will get cosine of theta. That will be equal to this one. So let's calculate it. Negative 220 multiplied by cosine 133 divided by 170 will give me 0.883. 0.883. How can I calculate for theta? Theta will be just arc cosine. So it is just inverse of. So when you take inverse of this one, you will get this one. Inverse of this one will give you theta. So inverse cosine of this will give me the theta. So take inverse of it, shift cosine, put answer. So the angle theta is just 28 degrees. So as you see from the first equation, I know the one of unknowns. And for the second axis, which is the y-axis, I can put Betty's force. Betty's force actually will be just minus Betty, okay? Just put it's B, okay? Put minus B because when you put sine of minus 90, you will get negative of this value. Negative 1 multiplied by this. So it's easy. So I will not put my just angles and sines for this one because it's vertical. But the other ones which are inclined, I must put our angles. So plus Charles, which is just 170 sine of Charles angle, and I calculate Charles angle. So it will be just sine of 28. What about Alex? I know the angle, which is 133. So I will put plus, and the minus will come from this cosine. So cosine of 133 will give me negative. If I put here negative, because I'm seeing that it is just going in the minus way, in the negative direction, so I will get minus, and if I put cosine of this one, I will get another minus, which will cancel each other. So I will get a wrong result. So always put positive, then put your sines or cosines. So this angle, which is starting from positive x, will give you the sine. So as you see here, I have negative, and the other negative is coming from this. So I got a positive value here. So in this case, we will get the same idea. So I will put Alex magnitude, which is 220, and put sine of this one. Actually, as you see here, in the x-axis, Alex is pulling in the negative direction. But for the y-axis, as you see, Alex is pulling upward. That means it's just positive. And Charles is pulling upward, is positive. So Alex and Charles are just together pulling upward and balancing Betty's force. And Alex's force in negative direction, balancing Charles' force in the positive x direction. So Alex and Charles balancing each other in the x. And in the y-axis, we have three components. Alex, Charles, upward are balancing Betty's downward force. So we will calculate for B. You will see that this will be go to the other side. So just will be equal to these forces, summation of these two forces. So B is equal to what? 170 multiplied by sine of 28 plus 220 multiplied by sine 133. So you will get 240.7. So 2 unknowns and 2 equations I can solve for net force. So let's move to the second law. Actually, the first law, we will not see any applications for problems because there is no mathematical relation. But for the second law, we will see some problems. Let me solve this question for the second law. So we have an elevator. And we have a guy here. So, and this man's mass is just 75 kilograms. So the weight will be equal to 75 multiplied by 9.8. So I will get the weight force. It's just 735 newtons. What is the acceleration? Actually, the 75 kilogram and standing on a scale in an elevator. Okay, so we have a scale here, which will just this is the scale, okay, which will measure the weight. Elevator notes that as the elevator rises, the scale reads 825 newtons. So, as you see, our weight was 735 newton, but the scale reads more than this one. How can it happen? How can it happen? The weight is increased. How can it happen? Actually, acceleration will change your feeling for the weight. Acceleration will change the weight situation. For example, as I said before, in the Earth we will weight just 9.8 times our masses. But in the moon, when you get a scale and put it in the moon, so you will see that you will scale just 1.6 times of your mass. So in this case, you are in an elevator, but actually because of your acceleration in changing, you will feel that you will be in a different planet. Okay, so if elevator is moving with an acceleration and is not moving with a constant velocity, that means you must feel a different weight. So this scale will read another weight, as you see here. So I can calculate for the acceleration. So let's take this scale. Let's take this scale and make a free body diagram. We have a weight which is acting down. We have a weight which is acting down. And this is the real case for the weight is just 735 Newton, right? 735 newtons. But since the normal force which is being applied by the scale to the guy for pushing this guy up to accelerate. Actually, when you have when the elevator accelerates up, scale must exert more force to the guy. Scale must exert more force to the guy, normal force, which makes the guy moves up with an acceleration. So the normal force, which is here, must be bigger than this weight because we are accelerating up. The question is not saying that we are accelerating up, but since the scale reads more than this one, I'm understanding that I'm going up with an acceleration. But if the scale reads smaller than this one, I will say that I'm accelerating down. If scale reads the same value, I will say that I'm at rest, or I'm moving downward or upward with a constant velocity. That means the net force in y equals to 0. But in this case, actually, the net force in y is not equal to 0. So normal force is equal to, the scale reads, so 825 newtons. So I will put the free body diagram, I put the free body diagram, so I'll put here the net force. It will not equal to 0. Why? Because this is application of second law, and in second law, if there is an acceleration, I might put my acceleration. For the previous for the previous problems, I put that the net force is equal to 0 because in that case it's given that our acceleration is 0. But in this case, I don't know what's the acceleration, so I must put the acceleration. Mass times acceleration in y. What about the mass? It's given, so 75 kilogram multiplied by ay. I must solve for ay. So the net force in y must be equal to 75 times acceleration in y. And these must be equal to the net force. I will put net force, which is normal force, minus this one, it's downward. So I will get 75 times acceleration in y will be equal to just this. So it is just 90. I will get acceleration in y. Acceleration in y will be equal to 90 divided by 75, which is equal to what? Just 1.2 meter per second squared. This is the answer. So if you have, if scale reads more, that means you are accelerating up. So you will feel more force. The scale will read more force. But if you are accelerating down, the scale will read less force. This is one of the applications for Newton's second law. So I have a car which has mass of 3,000 kilograms. That means 3 tons. So 2 forces are applied on the car or to the car. So what is the resultant of these 2 forces? How can I know the resultant of these 2 forces? So I must know what is resultant in x, and I must know what is resultant. Actually, resultant in x means this one, okay? F in x. I must calculate this one, and I must calculate this one. Then I will know what is the resultant force, actually the summation of these two. The summation of these two will be just equal to summation of x squared plus summation of y squared. So I will know what is the net force, the resultant force which is acting on the car. So Fx, which is this one, will be equal to just, let's put our angles. Here I have 60 degree, and here this one 90 plus 10. So this one, actually the biggest angle, which will be start from here until there, this will be just 90 plus 10, just 100 degree. So in x I will put 400 Newton cosine of 60. Then I will put the other force, which is 450, but cosine of 100. So these will be equal to what? Let's see. 400 cosine 60 plus 450 cosine of 100. So I will get 121.9 newtons. Actually, this must be equal to what? Mass times acceleration in x. But it's talking about the total acceleration. So I will not calculate the acceleration in x. I will calculate only acceleration in this resultant force, okay, in the resultant way, in the resultant direction. So the total acceleration I will calculate it by the last formula. But let's see that if I calculate ax here and ay here, then take square root of summation of square of them, I will see the same answer. So here just calculate ax. So ax will be equal to just the net force, which is this one, divided by mass, which is 3,000. So I will get what? 0.041 meter per second squared. So this is our acceleration in x. What about the y-axis? So here in the y-axis I have 2 forces, which the one of them is just sine of this one, and the other one just sine of the other one. So I will put them. So 400 sine of 60 plus 450 sine of 100 will give me the net force, which is just 789.6. That must be equal to what? M times acceleration in y. So acceleration in y will be equal to the net force, which is this one, divided by the mass, which is 3,000. So I will get just divide this one by 3000, so you will get the acceleration in y, which is just 0.263. Here, let's calculate the F, the net force, which will be the summation of these two. So that will be just the net force in x squared plus the net force in y squared so you will get just 798 point what, just say it's we can round it to the 700 what, 99, we can round it to 799. So I will take my pen. Newtons. What about the resultant acceleration? Resultant acceleration can be calculated by two ways. Acceleration in x squared plus acceleration in y squared. Or from this equation, I can say that acceleration, resultant acceleration, will be equal to the net force, which is this one, divided by the mass of the car. So I will take our calculator and divide this value by 3000. So I will get the resultant acceleration, which is just 0.266. 0.266. So try here to get the same solution, but with another way. So here I will get the acceleration in x squared plus acceleration in y squared. So 263. I will get the same solution. So let's see. Acceleration in x, which is this one, squared plus. As you see, I got the same solution, 0.266 meter per second square. So two ways. You can find acceleration in x by just taking net forces in x. So calculate for ax, then calculate for acceleration in y, then take result of them. Or you can calculate fx, just the value of fx, and fy. So take the resultant of f's, find the resultant force, then by knowing resultant force you can calculate for a, which will be just the resultant force divided by the mass. So this is the finishing of this question. But to know what is the direction of motion, what is the direction of the acceleration, actually we must calculate it also. So the angle which will be just arctangent of ay divided by ax, or it can be just arctangent of the net force in y divided by net force in x. You will see that when you take this one or the other one, you will take the same angle. So just try by acceleration. I have this acceleration in y, and the other acceleration in x is this one. So when I take the inverse tangent of them, I take this angle. What about when I'm putting the force values? So I will put here fx, which is just 121.9, and here fy, which is just 789.6. So you will see that actually they are nearly equal to each other because we made some roundations. When we take exact values, you will see that they are totally equal to each other. 81.1 and the other one 81.1. So they are exactly equal to each other. So you can apply one of these rules. That's it. But the angle between velocities vy divided by vx will not be equal to force directions. Why? Because the f net, which is this one, the f net vector, must be in the same direction of the acceleration vector, because they are just when you multiply this by mass, you will get the other one. Yes or no? When you just multiply acceleration by mass, so you will get this one. So they must be equal to in the same direction. But the velocity can be in this direction, or can be in the same direction, or can be in the other directions. So this is the idea and relation between the vectors of acceleration and force and velocity. Velocity don't have to equal the same angle, but always acceleration and force, they are equal to each other in the direction. So we finished now second law's problems, and I'll skip the problems for chapter 4.4 because it's just mass and weight, so there is no applicable problems. Actually, we are using mass and weight in our other problems. So here I'm using weight actually in second law problems, or in just in the net force problems, or in the free body diagrams I'm using the weight. But I won't solve some questions for mass and weight. And what about the fifth part, which is the third law? Actually, just to know every action has an equal and opposite reaction, it will be just enough. But you can see this problem. So as a homework, you can solve it by yourself. It's just an application or example for normal for reaction forces and third law. Or you can see this example in your textbook for understanding more about third law. But I will continue with just free body diagram part, which is the last part for chapter 4.6. So I will solve one more problem, then finish the video for chapter 4. You can see this this question as a homework. Okay, so the solution is attached. So if you want to solve this question, actually you can see and stop the video now and see the solution and try to solve this by yourself. And the second problem will be just this one. So please stop the video and take the picture and try to solve this by yourself. And I will solve this, the last question by just in this video. And the two questions which I showed here now will be your homework. So it's a cool application for free body diagram and to understand about the acceleration and the weight. Okay, so I will go up now. I will put my elevator. So it's about elevator. As I said, if you are accelerating with an elevator up or down, so that will be just as same as when you are in another planet. So the gravity will change because you are moving with a different acceleration from the Earth acceleration. Actually the gravitational acceleration. So let's see the example. A woman is standing in an elevator. So I will put the woman here. Okay. All right, it's just not straight line. So she is holding a briefcase. Actually, she is holding a briefcase. Just put your case here. Okay. And this briefcase has the mass of the case is just 2.6 kilograms. Okay, so weight of the case, so which is the force of the case which is pushing down, will be 9.8 times this one. So it will be just 25.5 newtons. So draw a free body diagram for the briefcase if the elevator is accelerating downward at this value, and calculate the downward pull of the briefcase on the woman's arm while the elevator is accelerating. So we must calculate, we must put the free body diagram and see what is the woman's force, which is the force coming from woman's arm. So that will be the weight feeling of the woman. So when we are at rest, okay, when we are at this room, so when this woman just carrying this briefcase, she will feel the exact weight, right? She will feel the same weight of this one. But if she goes to the elevator and push any floor, then she will observe an acceleration up or down. So if the elevator accelerating up, so she will feel a lot of forces. So that will be more difficult to carry this suitcase. Actually, if it's accelerating up with a huge amount of acceleration, maybe she cannot hold this suitcase. But if the acceleration direction was downward, let's say as the same amount of gravitational acceleration, actually that means when the rope is cut, okay, so when the rope is cut now, the elevator will fall down with a free fall, with a gravitational acceleration. So she will not feel any weight. She will just slightly carry this suitcase and will not feel any weight. So the idea is, when you are accelerating down in an elevator, the weights will be less. And when you are accelerating up, the feeling of the weights will be more, and so will be increased. So let's see the free body diagram for the suitcase or briefcase. It's just briefcase. So I have the weight of the briefcase here, weight, which is just which is just 25.5 newtons, and I have a force which is coming from woman's arm, which the force which is exerted by the woman. So let's put our tension force. It will come from muscles or normal force. Actually, it will be just normal force which is on the hand of the woman, but this normal force will affect her muscles. So let's put the other one, which is just F, which is pushing force from the woman's arm. How can I calculate F? As you know, it's accelerating upward, right? They are all accelerating upward with a known amount of acceleration. It is just 2.1. So when you take the resultant force in y, that they must be equal to m times acceleration in y. So the forces are F minus 25.5. So these must be equal to m times acceleration in y. And I will not take mass of the woman because I'm making a free body diagram for the briefcase. So I must take the weight of the briefcase. Weight of the briefcase, which is 2.6 kilograms, times acceleration in y must be equal to F minus this one. But I know the acceleration in y, so I will put the value. So they must be equal to F minus 25.5. So I can calculate for F. F will be equal to, just this one will go to the other side. So 25.5 plus this one. So I will get the answer 25.5 plus just 2.6 multiplied by 2.1 will give me the answer. It's just nearly equal to 31 newtons. So this is the answer, and we finished the question. Actually, as you see, the weight is 25.5, but the force which is exerted from the woman's arm is bigger. So she will feel a lot of, she will feel the weight more because she will feel just the applied force from her hand. So she will feel the force which is applied from her hand. So that means the weight will be, the feeling of the weight will be bigger for her. So this is the idea. But when the case is reversed, so we are accelerating down by this acceleration, so she will feel, this one will be negative, so this one will be negative. Let's calculate. This one will be negative, and this one will be negative. She will feel less weight. So as you see, just 5.5 newtons less. This is the acceleration, right? 2.1. Let's say that our acceleration downward was just 9, so very near to free fall. What will you see? You will see that actually you will feel just 2 newtons. So it will be very easy to just carry it. What about if you are accelerating up by 9 meters per second squared? So your case will be 48.9 of 48.9 newtons. So you will feel just like a double weight. So you will feel the weight as a double. So this was the last question for chapter 4. I finished this chapter. I hope that you enjoyed the lectures with me. So see you in the next chapter, which is chapter 5, and we will apply some Newton's laws in some other problems and some new different concepts, just the inclined plane and Atwood's machine. So please just keep following me, and inshallah we will finish chapter 5 with you in the next videos. So see you.